Hello, back to 8701. So in this section, we'll talk about relativistic kinematics. But let me start by saying that one of my favorite classes here at MIT is a class called H20, Special Relativity, where we teach students about special relativity, of course, but Einstein and paradoxes. And it's one of my favorite classes. And in that class, there's a component on particle physics, which has to do with just using relativistic kinematics in order to understand how to create antimatter, how to collide beams, how we can analyze decays. And in this introductory section, we want to do a very similar thing. I trust that you all had some sort of class introduction of special relativity, some of you maybe general relativity. What we want to do here is review this content very briefly, but then more use it in a number of examples. So in particle physics, nuclear physics, we often deal with particles which travel close to the speed of light. The photon travels at the speed of light. We typically define the velocity as v over c in natural units. Beta is the velocity. Gamma is defined by 1 over square root 1 minus the velocity squared. Beta is always smaller or equal to 1, smaller for massive particles, and gamma is always equal or greater than 1. The total energy of a particle with zero mass, with non-zero mass, is then given by gamma times mc squared. And the momentum is given by gamma times mv or gamma times m beta. The total energy squared of a particle, and we are considering one massive particle or one particle, is given by energy squared equal momentum squared plus mass squared. If you now consider a particle with zero mass, you see that the energy and the momentum are equal. If you consider a particle at rest, meaning the momentum is zero, you see that the energy is equal to the mass. So you get Einstein's famous formula: the energy is equal E equal mc squared. The energy is equal to the mass. So there's an equivalence between those two. What we want to fully understand and control are Lorentz transformations, are here shown for the example that we have a boost or a transformation in x direction. So you see that energy and momentum transform like time and space. And I really encourage you to just review this in more general cases, but you can always, when you have a boost in one direction, just do a rotation and get to this more simplified case. So here's the first example I would like you to actually go through. The Lorentz transformation here, I decided to use the z direction just to change things up a little bit. And the velocity of the boosted frame is vb. So we want to calculate the quantity m square c square in the transform frame. And what you will find if you actually do the calculation, and the solutions are in the backup slides, is that that quantity doesn't change under Lorentz transformation. It is invariant. And we'll talk about an invariant mass in this context. So now, in particle physics, we often have the case that we're not considering just one particle and want to describe this one particle or measure it, but often decays of particles or multiple particles which are involved in a reaction. So we can look at the total energy, just the sum of the energy of all particles, the total momentum, the sum of the momentum of all particles. And those two quantities are always conserved. They are not invariant. So be aware of the distinction between conserved properties and invariant properties. Invariant here means, we perform a transformation like the Lorentz transformation and the property doesn't change. Conserved here means we have a reaction, and in that reaction, the property is not changing. Those are two different distinct things. So now you can look at the invariant property, or the one which is conserved in this collision, which is this mass term or mass square term, the total mass. We just define this total mass as equal to the energy square minus the momentum square. And then we can consider the two cases of a laboratory frame and the so-called center of mass frame. So in the laboratory frame, We have a particle, it's moving. Now we observe this particle and then it decays into, in this example, 3 daughter particles. In the center of mass frame, in this example, we put ourselves into the rest frame of the particle we are interested in. And in that frame then, 3 particles emerge and we can describe the 3 particles. So momenta between the 3 daughter particles are not going to be the same. But because this total mass is an invariant property, it's the same in both frames. And it's equal to the mass of the parent particle which we decayed. So when you measure the energy and momentum of the daughter particles, you can infer in any frame the mass of the parent particle by calculating the total mass. And so you can infer from those measurements the identity of the mother particle. And that's, for example, how we discover the Higgs boson. We measure the Higgs boson decay into a pair of photons, and then we calculate the mass of those 2 photons in our laboratory frame, and that mass then is equal to the Higgs mass. So now here we want to compare or look into those 2 cases a little bit more. The first case is a case where we have a particle 1 colliding with a particle 2, where the particle 2 is at rest. Particle 1 has a certain energy, E1. And the second example, this is called a fixed target experiment. So the second particle is fixed, the first one is colliding. The second example is the one where we have 2 particles and both have energies and we bring them to collision. Often the 2 particles are of the same nature, like 2 protons, 1 electron and positron, and the energies of the beams are the same. But this doesn't have to be the case. Later in the class, we'll look at heavy ion collisions, so the collision of heavy ions like lead with a proton. And here the masses are different and the energy of the particles can be different. All right, and here's another exercise now. So we want to actually create a Z boson, which has a mass of about 91 GeV. Note, I dropped the C square, 1 over C square here. And you want to produce this particle by colliding a positron with an electron. So this has happened at lab at CERN in the late 80s and 90s. The center of mass energy, often also called square root S, is equal to 91 GeV. So that's the energy we need in order to produce this new particle. The mass of the electron and the positron are 511 keV or 0.511 MeV. So the energy needed is 45 GeV, 45.5 GeV. However, that was the setup at lab where you have 2 beams colliding. So we have this center of mass energy being given by the energy directly given approximately by the energy of the 2 beams. So now imagine somebody would have proposed a fixed target experiment where you have stationary electrons, for example, electrons in atoms, just a gas of some sorts, and then you have produced positrons in a beam, accelerate them and bring them to collision. So the question here now is, how large do you need an energy of this positron beam? How large does it have to be in order to produce a Z boson? So again, this is something I would like you to actually explore and just write down. Solutions for this example are also in the backup. So now, there is a number of interesting examples just coming from E equal mc square and from being able to use, and they can be answered by being able to use Lorentz transformation. And so now here I give you just a set of examples, and you should work on them on your own time. Maybe we'll touch on them in recitation. The first one is rather straightforward. Again, we're talking about lab at CERN. After the Z bosons were produced, one was trying to go to high energy to find some new physics, some new particle. For example, the Higgs boson. The Higgs boson might be produced by a process which is called Higgs-Strahlungs process. We will look at this later. So you have an electron and a positron colliding to a virtual Z boson. So that is a Z boson which is heavier than 91 GeV. We'll see later how that's possible. But then that virtual Z boson can radiate a Higgs boson. So that's why it's called Higgs-Strahlung, like the German word for radiation, Strahlung, the process. And so electrons and positrons were accelerated to 100 GeV each, center of mass energy 200 GeV. What was the gamma factor for those electrons? Another question, which is quite exciting, is how much energy do you need in order to split a proton and a neutron, which is a bound state. It's called a deuteron. And it's a fundamentally important particle in the evolution of our universe, in the sense that in order to generate higher mass or higher proton number elements, a deuteron is rather important in this. And so just by knowing the mass of the proton, the mass of the neutron, and the mass of the deuteron, you can now calculate how much energy is in the binded, or what is the binding energy between those particles. We'll talk a lot about models to calculate binding energy when we talk about nuclear physics, but here just from the kinematics, you can, and from E equal mc squared, you can calculate how much energy needs to be in this binded or compound state. From atomic physics, you might remember or know that excited particles can emit photons. And so now you have a particle, it de-excites, it radiates a photon. What happens now to the photon? Imagine this is happening in a big gas or in some solid state. Can the photon be reabsorbed by the same medium or even by the same particle? It's not a trivial question, but what is the condition under which, so for example, imagine you have a gas, there's an excited particle in it, it emits a photon, and so now the photon sees the rest of the gas. Can that rest of the gas absorb the photon? Interesting question, it's not trivial. Another interesting question, I think, is, you're trying to produce new forms of matter. Like you just produced the Z boson, but you can also produce antiprotons. So what is the minimal energy in a proton on a fixed target experiment? So again, you have a target of protons in some form. You shoot a proton against this target and you try to produce an antiproton. So that means that you have to produce, in this collision, you have two protons in the initial state. You have to have a proton, another proton, and an antiproton in your final state. But how much energy is needed for the proton beam in order to succeed with this collision? My counting is incorrect here, so this should be 5, but okay, fine. Decays. So assume a pion decays at rest. So a pion is at rest. We looked at a pion, that's a compound state, a meson, out of an up quark and a down quark, and it might decay into an electron and a positron. Whatever the dynamics is in this decays, if you just look at the kinematics of this, how fast are the decay products? In order to calculate that, you need to look up the pion mass, the electron mass we just discussed, and the positron has the same mass. So how fast are electron and positron coming out of a pion decay? Assume that the pion is at rest. Then you can use momentum conservation and calculate the speed of the electrons and positrons. Again, one of those minimal energy proton colliding experiments, very similar setup, but here we try to produce a proton, a neutron, and a pion out of proton-proton collision. And then the last one is the so-called Compton effect, where you have a photon which scatters off an electron target. And so you have an incoming photon, an electron is at rest, and then you look at the scattered photon angle, the scattered electron angle, and in that collision, the energy of the photon is going to change. So the energy of the photon is h times nu, or h over lambda, the wavelength. And so the question is, how does the wavelength of the photon change in this kind of collision? So those are just examples in how you can use relativistic kinematics in order to calculate very important aspects of collisions in particle physics without any understanding at this point of the underlying dynamics, the underlying forces, the underlying conservation laws, and so on. So later in this class, we discuss what is the likelihood of a pion to decay into an electron positron and why that is actually not that likely. And also the collision rates, lifetimes of particles. But here we are just looking at the kinematic of those processes and calculate how much energy is involved and or to the momentum of resulting particles. So I'll stop here. If you scroll down on the slides, you find solutions to 2 of the problems, and we'll discuss them in recitation.